we're going to take a look at a few functions that we talked about last time. So we're going to be transforming them. And we have sine theta and cos theta. And if you recall, we'll jump over here. When we put those into decimals, so I'll use x as the theta instead of the variable theta. But these are the general basic versions of sine and cos when there's no transformations applied to them, okay? I'll hide cos for now. Recall that we're actually being measured in radians at the moment, okay? So to make a full rotation or an entire period of a sine function is 2 pi. So halfway is pi, okay? And we usually start at 0, 0. Where cos, a little different, it's, since 0 is actually at 1, yeah, sure. Yeah, that's it. Okay, so this one's period takes 2 pi also, so it's a lot. It's the exact same period. The only difference is it looks like we're starting at peaks and there's a little trough down here. So it's the same period, but instead of starting at the middle and going up and down, we start at the top, we go all the way down and come back to the top again. You kind of want to get into the habit of memorizing 5 major points of these functions. And the reason is just because these, you'll want to know how to draw the originals of them. So your cos starting at 0 and 1, and then ending at 2 pi and 1 again. That coordinate, these 5 coordinates here, so 1, 2, 3, 4, and 5, are pretty important to remember. So if you can memorize them, it makes transforming the functions much, much easier. Same idea with your sine. It starts at 0, 0, okay? So memorizing these little parts here can be very, very handy. What we can do is we can actually add little tables, and these tables can come in pretty handy for memorizing our information. So okay. Do is we'll put in the x values, pardon me, and they'll give us these 5 coordinates down here. So instead of just using what we had before, what do we have as our radians here? Pardon me. We have pi over 2 as an option. So I'm going to actually have to use this little keyboard down here to type. Oh, no, never mind. It's down here. Divided by 2. So you'll notice they give us some very distinct values, which is what we're going to need to memorize. And this one's going to be 2 pi. Okay, so these are the 5 major coordinates for your sine wave, and for your cos wave, we'll use the same x values. And as soon as I'll get rid of this keyboard in a second to make it a little easier to read. 3 pi, divide 2, and then finally 2 pi. All right, let's get rid of that keyboard. Okay, so these are your 5 major coordinates. So having them in mind when we're going through transformations of sine and cosine will be very, very handy. So we'll keep these handy on the side here, and we'll jump back to this page that we were working on. So what we want to show you is there's kind of like a general function to a sine wave. So we'll say something like y is equal to, and we'll use different colors to help with the different values. So you have a, we'll use sine for now. You would have been used to, because you've done function notation, technically, I mean, this shouldn't be too foreign to you, but we'll substitute sine and cosine. You have a, you have b. They've been using, they use x in here instead of theta, so we're going to do the same thing. I'm going to say x plus, we'll use another color for c, and then outside the function again is the value of d. Okay. Now we used f and x in here, but we can actually just as easily say y is equal to a sine, and then we have in brackets here the letter b, and all we're doing is kind of showing the parent function to this. We'll add in c and d on the outside, And the same concept, without rewriting everything, we could just write in the word cos, and everything else is technically the same there. What's important here is trying to figure out what these values do. If you remember quadratic functions, your a value here has to do with vertical stretches and compressions. So we'll say SNC. And it's just we're going to pull something upwards. Think of it like we're pulling something up and down. Remember, a periodic function has this, so we start pulling the extremes up and down. Okay. The b value actually has to do with horizontal stretches and compressions. We didn't really deal with that with quadratic functions. And the reason being is that a vertical and horizontal compression look almost the same with a quadratic function. But for a periodic function, it's the concept of like putting the period or the waves, they look like they get scrunched together. So think about horizontally pushing it in and out, like like an elastic band, or vertically going up and down. So that's what the a and b values do, depending on what whole number or what numeric value they have. The c value is again horizontal. It's horizontal. Yeah, of course. These ones have to do with horizontal transformations. And what that has to do is moving the entire function to the left or to the right. So not actually manipulating how it looks, but moving the whole thing left and right. And then finally, D has to do with vertical translations. And it's the same idea. You take the periodic function, but you're just going to move it up or down. Okay? These are the spaces. We've kind of given you a parent function in here. These are the places you'd find values for them. And you'll notice we have two little examples down here. But what I'm going to do is I'm going to give a couple of other examples, and then we can answer these as questions ourselves. I'm going to jump back into Desmos very quickly. And just because what I want to show now, and I'm going to turn these two off. If I do sine x, that was our original function we had. I'll get rid of these things here. With sine x, I can transform it. So I'm actually going to give now 2 sine x. And what I want you to notice is what happened here is this was pulled upwards, okay, and pulled downwards. Notice the zero values are the exact same. Nothing's happened to these zero values, but the peak and the trough, so high, the max, and the min points have become more extreme. They've actually been pulled farther down. Recall that this value used to be some x value and 1. It's actually now at the y value of 2. If I were to draw a line across, the highest point is now 2, and the lowest point is now negative 2. So what we've actually done is we've multiplied by the value of 2. We've multiplied whatever the y coordinate was originally. So whatever that y coordinate was, we multiplied it by 2 to get a stretch to this object. Okay? We can also compress the same object. So let's turn that one off. And we're going to say sine 2x. Okay? So this is a horizontal compression. Okay? Now notice I put the 2 in a different place than the other one was before. And what has happened is the period has occurred twice as often. So remember in the blue one, and it's a little hard to see, this is an entire period. It's the considered 2 pi to make an entire rotation. But in this new version, you notice that this coordinate is actually pi. So the purple goes up, back down, and back to the beginning again. So its period is twice as often as it originally was. We can now get 2 periods in the same space that we would normally only get 1. So all of our x values have been changed by the value of 2 here. Okay, so think of it like this. If the final x value here was 2 pi, we divide that by 2, which was that value down there, and 2 pi divided by 2 actually gives us the value of pi. So we take all the x coordinates, whatever they were. For instance, one of the x coordinates used to be pi divided by 2, and we divide that by 2. We actually end up at pi divided by 4, a quarter pi, and that's actually this coordinate down here. This is now at pi 1/4 on the purple. Okay, so we've compressed everything, and we can get the exact opposite to that. We can change it, and I'll show you that with a little scale option later, but let's just talk about all the 4 different translations that we can potentially do. So we'll turn this one off. Another one was sine, and then in brackets x, I'm going to say plus, and we're going to use the value of pi since we're in radians. Okay? So you'll notice this one has a really nice visual effect to the original, but what's actually happened is we've taken the original coordinates, the original x coordinates. So remember, this one was at 0, and this one, so the blue one is our original, so I'll highlight it in red so it's a little different. Here it is, and what we've done is we've shifted everything pi units. Okay, so this used to be 0 and 0. It's now been shifted to, pi and 0. And it's a little easier to notice the peak. This is the peak here. Remember, this peak used to be at pi over 2, comma 1 was the coordinate. It's now been shifted to 3 pi over 2 and 1. So what we did is we shifted everything. The frequency and the maximum and minimums haven't changed, but we've shifted the entire wave, the phase shift, I'll call this, either to the right or the left, depending if it's positive or negative. Okay? And then finally, the last major translation we'll do is we'll say sine x plus 2. And all we've done here, same concept, the function itself has just shifted upwards, has a vertical shift of 2 units. So this was at 0 and 0. It's now at 0 and 2. So we added 2 to the x value, just like we had added pi to the x value in the previous phase shift. This one's just taking the y value and adding a number to it. So another way you can look at this stuff, and I usually find this one the best one to look at it, is I'm going to write it out here. A sine bracket b bracket x plus c. Oh, got too many there. Plus d. Okay, I'm going to make sliders. They call these, and the a slider is going to be 1. The b slider should be 1. The c slider should be 0 to start, and the d slider should also be 0. Okay, so if you notice, and they're both blue. They happen to both be blue in this sense. I'll turn this one off. This function is exactly where the original one was, right? We have the exact same 5 major coordinates. What we can do is if I move the a value to a greater value, so you'll notice it goes towards 10, it starts to stretch up. And as it comes back down and goes negative, it flips and goes in the other direction. So this is what a vertical stretch looks like. So what it's doing right now is just going through a continuum of numbers between negative 10 and 10, but it's trying to give you the idea those z values, or the axis, the equation of the axis, that stays the same, but the max and minimums are what are affected by this a value here, okay? I'm going to change the a value back to 1 because that's its like standard spot. Is equal to 1. The b value, I want you to see that as we change that, there's your phase shift. So it's like an accordion going in and out. So as we make it negative and positive, flip the phase shift, but as we make the number greater, you'll notice that the phase shift gets much more frequent. And as we get between 0 and 1, it gets stretched out quite a bit. But this is the idea of a horizontal compression or stretch. Okay, we'll change this back to 1 also. That's what it originally was. C value has to do with horizontal phase shifts, or sorry, not phase shift, horizontal shifting of it. So you notice it's going to go to the left, and then it's going to go back to the right. Okay, so back to the left and back to the right. So that's all this function is doing, one way to the other. As you increase or decrease that number, it just moves it along the x-axis, okay? And then finally, let's give this 0 again. We have d. This gives you the vertical translations, so moving it up and back down. So the actual frequency of everything stays the same. It's just the vertical translation of the object going upwards if the number gets higher, or heading back downwards as it gets lower. And I'll put that back to 0. Okay, so